last class we were talking about precipitation. There is one concept in precipitation which we have not yet covered. I thought today we will talk about it, that is coarsening, particle coarsening. Let us say people also call it as there is another name for this. Anybody has heard of it? Any precipitates, when you heat them to higher temperature, take the alloy to higher temperature, the precipitates coarsen. This phenomena, there is a name generally used in edge hardening. What is it called? The phenomenon. Yes, somebody said something. No, it is called Ostwald ripening. Ripen, yes. So this is, both are basically refer to the same concept. So if you look at why should particles coarsen, all of you know, yes, whenever the temperature is high, diffusion is there, so there is a growth. But at the same time, if you look at if all the particles are of the same size, if you assume that there are a number of particles inside the material, all precipitates, and all of them are of the same size, then you would never see any particle coarsening. Particle coarsening happens only when there are particles of different sizes, and in fact some particles dissolve, decrease in size, and some particles increase in size. This is the basic phenomena of coarsening, and we will understand that if you understand again the same free energy concepts. If you look at a material, let us say this is one grain and you have particles of different sizes, something like this. You may ask me, sir, how do you get particles of different sizes? When do you get particles all of them are of the same size? Can you tell me? If there is a homogeneous nucleation at some time t equal to 0 and there is no further nucleation after that. Nucleation is a transient phenomenon, and I told you that there are different hierarchy of sites where nucleation can happen. For example, nucleation can happen on the surface first, and then we talk about grain boundaries, isn't it? Then you talk about stacking faults, dislocations and vacancies. So there are variety of places where nucleation can take place, and once certain nucleation sites are occupied, then you start seeing the other nucleation sites start becoming active. The nucleation sites with the highest energy, once they are all occupied, then the nucleation sites with the lower energy, lower with respect to the highest energy, will start working. For example, if the surface is there is for some reason it is not possible to nucleate on the surface, or if the surface is fully covered with the nuclei, then as a function of time the nuclei which have formed on the surface will start growing, and at the same time further new nuclei you will start seeing them either at the triple junctions or at the grain boundaries. And if once they are covered, then you may see that as they start growing you may see further nucleation taking place, maybe at the stacking faults or at the dislocations. So you will see that nucleation is not a kind of a phenomena where everywhere it happens at time t equal to 0 and all of them start growing at the same rate. If that happens, then you would see a situation, this is what we call it as site saturation. When all the sites are saturated at the same time, at time t equal to some t, whatever time it is, and then all these precipitates start growing at the same rate, then you can assume that all the precipitates are of the same size, which is a very ideal situation. It never happens that way. So you will see that as a precipitate which is nucleated at some site starts growing, there will be further precipitation at some other sites, and as a result you will always see a distribution of particle sizes. Whenever you see precipitate particle size distribution, if you try to measure, you will always see a distribution. There will be smaller particles, there will be bigger particles, and you can talk about what is the average particle size. That is why we always talk about average particle size, because we know pretty well that they are all of not the same size. Once you talk about this kind of a distribution, and then you are heating this to a higher temperature. Let us say all this kind of precipitation has taken place at some temperature, let us say during natural aging or artificial aging, and in service this material is being exposed to a higher temperature now. If it is being exposed to a higher temperature, this kind of microstructure, how does it grow? We know pretty well that at high temperature you are providing sufficient thermal energy and thermal activation for the diffusion to occur. So, there is a possibility that all particles can grow, but do you see all the particles grow or not? So, that is where if we try to understand this precipitate which is in equilibrium with matrix and this precipitate which is also in equilibrium with matrix, if you look at the matrix composition which is in equilibrium with this precipitate and this precipitate, it is never the same. How does it come out? I would repeat that the matrix composition, the composition of the matrix which is alpha in our case, and let us say this is, you call it as a theta, whatever precipitate it is, the composition of alpha in equilibrium with this precipitate, it is the same theta, this is also the same theta. The composition of alpha in equilibrium with this theta is different from the composition of alpha in equilibrium with this theta. Why does this happen?
The composition around that theta copper will be less.
Why?
Because the diffusion has occurred for a longer time.
It has nothing to do with diffusion. It is the curvature effect. Because of the curvature effect, you would see actually the free energy of that two particles is different. You always see whenever we are talking of a free energy diagram, we always talk about volume free energy only, we do not bring in the surface free energy term. That is why if you look at all the free energy composition diagrams that you draw, you assume that the precipitate size is infinite. Actually precipitate size is not infinite, and different precipitates will have different free energies, though they all have the same structure, same composition, because the surface energy has to be added to the volume free energy, so that you actually talk about the free energy. So, a smaller particle always will have a higher free energy when compared to a larger particle, and if that is the case, if you draw that Gx diagram, let us say this is the free energy composition diagram, this is of alpha, and this is let us say theta phase with a larger particles and theta phase with a smaller particle. This is, you can call it as a smaller particle, this is a larger particle. So, a smaller particle will always have a higher free energy when compared to the larger particles, and if that is the case, then if I draw now a common tangent, you would see that this concept which I just now said, that the composition of alpha in equilibrium with a larger particle is different from the composition of alpha in equilibrium with a smaller particle. So, this is the composition of alpha in equilibrium with theta, which is let us say larger, and similarly this is the composition of alpha in equilibrium with theta, which is smaller. The moment that is the case, then if I now simply look a smaller segment of where you have one small particle, one large particle, and there is alpha in the middle, the composition of alpha which is just in front of this particle, the composition of alpha which is just in front of this particle is different, and which is higher? The smaller is the higher. So, if I now draw what is called the compositional profile, how would the compositional profile look like? The theta phase, what is the composition of theta phase in aluminum copper? Al2 Cu or CuAl2, am I right? And what is the composition of alpha? That is the composition with which you have started, and we are talking about the starting composition, alloy composition is somewhere here. that is the alloy composition with which you have started, which will be a two phase mixture, and what we are talking about is the equilibrium composition of alpha. That means if you look at the phase diagram, this is let us say alpha plus theta here and this is alpha. So, we are talking at any given temperature this composition. This composition that you are looking at, of course, this is a temperature versus composition diagram or Tx diagram if you want to call it, because we called a Gx diagram. This line, what is this line called? Solvers line. This solvers line is always assuming that the theta has an infinite size. Any phase diagram, any solvers line that you see, okay, the assumption is that the second phase and the first the parent phase, both are, parent phase is anyway a matrix. So, you can't talk about a size of it, and there also in principle if the parent phase is also a nano grained alpha, let us say, it would definitely have a different free energy. So, there also we always assume that the grain size of alpha is infinite and also that the precipitate is also almost an infinite size. The moment you bring in size effects, this is what we call it as size effects, then you will start seeing that the free energies start shifting. The alpha also, instead of an alpha of a very large grain size, if I now start looking at nano grained alpha trying to precipitate out of the theta, then the alpha free energy curve also will shift. So, nano grained alpha will have a definitely a higher free energy with respect to an alpha of a much larger grain size. So, all those things are what we call them as size effects. So, this solvers is in principle for an infinite, and the moment I assume that the theta has a smaller particle size, you would see that particle, that composition will be different, and that if I try to draw, you would see that if I draw composition. So, let us imagine that this precipitate has certain composition. This is the composition in terms of percentage copper. If I plot, this is some value, let us call it whatever Al to Cu composition is. In terms of weight percent, it is approximately let us say 55%. Now, this is the composition of alpha somewhere here, which is usually just for the sake of understanding, let us again take this, the composition here also, this composition again this precipitate, inside the precipitate it is the same composition, it is the same theta, this whole thing is theta. So, the composition of the theta is this value. So, inside the theta the composition is this, and then if you look at this is the alpha composition here and the alpha composition here will be different. So, there is a gradient here inside this. So, if I look at the concentration profile, it looks like this. If I start from the center of the particle to the center of the particle, let us not bother about the other sides, because on this side there may be another particle, on this side there may be another particle, we will not bother. So, we simply look at from the center of this particle to the center of this particle. If you simply look at the composition profile, this is how you will see. Inside the alpha there is a gradient here. The smaller particle, the alpha which is in equilibrium with smaller particle will have a higher composition, the alpha in equilibrium with a larger particle will have a smaller composition, and once you have a gradient, you always have a diffusion, you will always have a flux at any given temperature, because flux is J equal to correct minus d into dC by dx, and that dC by dx you can see here, the x is nothing but the interparticle distance. Once you know the interparticle distance, you can talk about what is the dC by dx, and at any given temperature d can be known. So, you can actually see, and how does, what is the result of this diffusion? You see that copper atoms which are here want to diffuse towards this, but you need a constant supply of copper atoms for the copper atoms to go down the drain, down this particular decreasing concentration gradient. Where are the copper atoms coming from? The copper atoms come from this particular particle. The smaller particle provides the reservoir of copper atoms, so that the copper atoms start moving to this direction, because the theta has a higher copper content. So, this theta rejects some copper atoms by dissolving by a small amount, small delta x of this theta. If it dissolves, let us say, what happens? Some copper atoms are released, and those copper atoms will move down this concentration gradient and come to this region, and once they reach that region, this particular theta needs copper atoms for it to grow. So, it provides copper atoms. Once the copper atoms come towards this, they join this particular theta, and the theta grows by a small delta x, depending on how many copper atoms have come and joined. So, this gradient will more or less remain the same, excepting that the concentration values, this value and this value, what do these two values depend on? Radius. So, as the radius of these two change, in principle these two values also will change. As this particle becomes smaller and smaller, as it shrinks, what happens? So, you can see as this particle shrinks, this free energy goes up. If this free energy goes up, the common tangent starts touching it at a composition which is farther, which is higher in copper content. So, that means you would see that this value keeps going up. And what happens to this? As this starts becoming larger and larger, this value free energy comes down, and that means the common tangent, again the copper content of alpha comes down. That means you actually see that the gradient is increasing, because the dc delta c, which is nothing but the composition of alpha in equilibrium with the smaller particle, smaller theta, theta smaller, minus composition of alpha in equilibrium with theta that is larger, this delta starts increasing as the smaller particles start becoming smaller, the larger particles start becoming larger. So, in the process what happens is, slowly smaller particles will dissolve. At the expense of these smaller particles, the larger particles start growing. It is like we see that in a typical life, the bigger ones try to grab the smaller ones. So, exactly the same thing is happening here. The bigger particle is just growing at the expense of the smaller particle, and the whole thing, the whole driving force for such a thing is coming because of this free energy. So, once you understand this free energy, that the free energy of different particle sizes will be different, and you can easily understand why this is happening, and this gradient starts increasing. And of course, the distance, you may say what is going to happen to the dx, dc by dx, when you say dc by dx, this theta is growing and this is decreasing. So, in principle they may remain the same or can change by to some extent, okay, but we do not know what is the rate at which this decreases, what is the rate at which this increases. So, there may be a small change in the dx also, but dc you can see a significantly a large dc, and because of which more and more. So, as the time proceeds at that temperature, you will see the flux, the rate at which the atoms move is going to be higher and higher. This is usually against the normal case of precipitation. In a normal precipitation, how does the precipitation happen? If you look at the precipitation concentration gradient in precipitation, so the moment the alpha, if you take alpha, inside alpha, the moment a small nucleus precipitates, okay, a small theta precipitates, how does the further growth happen there? The further growth happens again because of the gradient. Where is this gradient coming from? So, the alpha that you have is the starting alpha is this alpha, am I right? That is 4% copper. The moment a theta is precipitated inside the alpha which can be in equilibrium with the theta is not this alpha. This 4% alpha cannot be in equilibrium with theta. Why? Because if I take the, forget about the smaller particle, let us look at the larger particle, okay, as the equilibrium particle, or you can choose any of them. So, in principle, if you look at this particle it cannot be in equilibrium with this, because you cannot draw a common tangent between this point alpha of that composition with the theta. The only equilibrium that you can have is with the theta with some other alpha, and that is what we call it as a composition of alpha in equilibrium with the theta, and that composition is different from this theta with this starting alpha. And as a result, if I now draw again a concentration profile, so if I take a small theta, this is let us say theta, whose composition, if I plot percentage copper, whose composition is again the 55% let us say, has nucleated, and now the composition of alpha just in equilibrium with theta, that means the alpha composition which is adjacent to the theta has a different composition than the alpha composition which is far away from the theta. The composition of alpha which is far away from the theta is this composition, the starting composition. The composition of alpha which is adjacent to theta is a different composition, which is lower, which is higher. Yes, adjacent to theta is a lower copper content, because of which you will see, I mean I have really exaggerated, it will not be like that, because this is 55 and this is actually 4%, something like this. This is the percentage of copper, this is the alpha of the initial alpha, the alpha with which you have started. You have taken an alloy of 4% copper, made it into a solutionized condition and then quenched it, and from there the actual precipitation has started, and that particular alpha is that 4%, but the alpha which is in touch with the theta is actually smaller, and because it is smaller, now you see there is a gradient here, and because of the gradient what happens is this copper which is there in alpha starts moving towards the interface, and once it starts moving towards the interface there are some copper atoms get accumulated at this, and once the amount of the copper atoms is sufficient for the theta, because theta is 55%. So, as the copper atoms keep coming towards theta, once in a small region the copper atoms reach 55%, that small region gets converted. Now, it is like almost like alpha of 55% copper gets converted to theta of 55% copper. It is like almost like a polymorphous transformation, allotropic transformation kind of. So, once the copper atoms reach that concentration level, it is only a structural transformation now. A FCC structure changes to a theta structure. So, as the copper atoms get accumulated in that small region, that small region gets changed to the theta, and as a result now the theta grows by a small distance. But in the whole process, because the whole precipitation is happening at a fixed temperature, this value will never change, because this value is coming from the free energy diagram, and in the free energy diagram the free energy diagrams are always drawn at a fixed temperature. At a fixed temperature the composition of alpha in equilibrium with theta is fixed, provided the theta size has not changed to such a significant extent that its value can change. If the theta size changes, we can expect that this value also can change, otherwise you can say this value is fixed. Once this value is fixed, what is that is changing as a function of time in this whole process? You have atoms of copper coming from this region towards this, and then theta is growing, and this is fixed, and then what changes? The composition of alpha in the matrix, what happens to it? It decreases, because the copper atoms are being released from here and coming here. So, the alpha concentration decreases, and once it decreases, what happens to the gradient? Gradient decreases, and as a result the process becomes slower. The reason why I had to tell you is that is which is reverse of this. So, as a result you can see as a function of time you will see.
Sir, when theta starts growing, still further nucleation takes place?
Yeah, I am not talking about that situation, you know, this is we are talking of one particular theta with respect to its alpha. How does this grow? There will be another nucleation somewhere else, at that region also similar thing will happen. As this theta wants to grow, the theta can grow only when copper atoms come and join to theta, otherwise theta cannot grow, because theta needs 55% of copper atoms. So, unless they are supplied to that interface of the alpha theta interface, the theta cannot grow. And where do these copper atoms come from? They cannot come from the thin air, they have to come from the alpha only. And as the alpha supplies more and more theta copper atoms, alpha gets depleted in copper.
How it can cause further nucleation when it starts growing?
No, this is we are talking of a small region, very small region, okay, and there can be some other region where, see, this whole thing is happening in a region of few 100 nanometers, and in a alloy, okay, the grain size itself is very large, 100 microns or so. So, in some other corner of the grain you can have another nucleation event can happen. So, we are talking of that particular, because the theta in the beginning is about 10-20 nanometers, and that particular theta, how is it growing, that is what we are looking at. So, as a result, after some time the whole thing would become like this, the theta would have grown to a certain extent, and then the alpha composition comes to that of the equilibrium composition. That means, there is no more excess copper left out in the alpha to be supplied to the theta. So, now the growth stops. Once this happens, the gradient is 0. Once the gradient is 0, then there is no flux, and if there is no flux, there is no growth. So, this is how the actual precipitation takes place. This vis-a-vis the next topic that we are going to cover, what is called spinodal, you will see there is a lot of difference between this and the spinodal. We will talk about it in a minute. So, is this clear now? So, how do precipitates grow? Yes. Why this is lower compared to this? Am I right? So, okay. So, the point is, if I look at, let us not talk about all this. Imagine I have started with an alpha of certain composition. This is a 4% copper. I started with this alloy, and I am holding this alloy at some temperature. I am holding this alloy which is solutionized, brought to this temperature, quenched, and I am holding at that temperature. At that temperature, is alpha stable? It is not stable. So, alpha as a single phase it is not stable. Be very specific when you say alpha is still stable. You still have the under in the equilibrium phase diagram you have alpha plus theta. We cannot say alpha is not stable. Alpha as a single phase it is not stable. Alpha can coexist with theta for that particular composition for that temperature. And now, if it is not stable as a single phase, it wants to precipitate. How do you understand this precipitation? Simply draw a tangent. If I draw a tangent at that composition, then what are all the phases whose free energy is below the tangent? All those phases can in principle nucleate. Let us not now consider about all the various phases that are possible, just look at only one phase, call it as theta phase, and that theta phase, the moment I look at this particular theta at that temperature has a certain free energy, and the moment there is a driving force, this theta will nucleate. The moment the theta nucleates inside the alpha somewhere, either grain boundary or wherever it is, the moment it nucleates, this alpha, this theta cannot be in equilibrium with this alpha. It is impossible that you can have a common tangent between the two. So, then what happens is, you will see that this theta will find out some composition of alpha with which it can be in equilibrium, and what as a result the alpha which is adjacent to that theta will have a different composition. In fact, this can be even physically understood. See, when you think of a theta being nucleate inside an alpha, okay, theta having a higher copper content, what happens is copper atoms get accumulated in a small region, and that region gets converted to theta. That is what, if you want to call it as a nucleation event, then they are getting accumulated from alpha. So, the region adjacent to that obviously is depleted. That is what is this depleted region, and this depleted region is having a different composition. So, the alpha which is in equilibrium with theta is having a composition which is lower, and the alpha which is far away from this nucleation site is actually having the starting composition. The starting composition is this, and the composition in equilibrium is this. This is what we are talking of the gradient. If this difference was not there, there is no gradient. Clear?
But the theta immediately after it splits, the grain size is very small.
Yes.
And then the free energy should be higher.
In principle, you are right, very right. So, in principle, if I consider that the theta is very small, you can actually draw the free energy curve of theta which is much higher, and see that the common tangent with that particular theta can be almost like, if this is the theta have at the nucleation site stage, you can actually draw a common tangent between that theta and the alpha starting alpha itself. This is assuming that particular small amount, okay, but this is only at the nucleation event. But when you want to talk about what is the overall driving force for the nucleation, overall driving force, you should always consider the theta after it has grown. After the whole precipitation process is over, when you are looking at the microstructure, what is the theta, and that particular theta with if you compare that theta, which is what we calculate only from the bulk free energy point of view, where surface energy is not considered, that is turns out to be this. This is only the volume free energy, this plus the surface energy. So, this whole thing is, you can say delta G surface, or you can call it as gamma if you want to call it, corresponding to that particle size of whatever is the initial particle size. So, the free energy gets lifted because of the surface energy, and at that particular moment you can say yes, it is in equilibrium, but the moment it grows to even a smaller extent, it cannot be in equilibrium with that. So, we are now looking at only, that is the reason why you have to see that most of the free energy composition diagrams are always drawn only considering the volume free energy. Capillarity effects or the surface effects are not considered, and once you start considering, this kind of concepts come into picture. In principle,
In this case, we have seen that we have considered the size factor.
correct, that is because there is a size distribution. If there was no size distribution, we would not have considered size effect. Because there is a size distribution, you wanted to know which one will grow, this will grow or this will grow. So, only if you understand that, you will understand this. Otherwise, when you are looking at one individual particle, you need not have to consider its size effect. Okay. Now, let us come to the next concept, which is similar to a precipitation, which is what we call it as spinodal. Spinodal decomposition. Let us try to understand what are the free energy concepts involved in this. As you can see, this we call it as decomposition, we do not call it as a precipitation. There is a difference between a precipitation and a decomposition. What is the difference? When you say decompose, what does it English term in yeah, something is splitting into two, that is what we call it as a decomposition. When you say precipitation, basically something is precipitating out of something else. So, there is a matrix from which some precipitate is coming out. Here when I say decomposition, a matrix is splitting into two, that is the meaning of decomposition. Let us try to understand that, and you will see that spinodal decomposition always occurs when the phase diagram shows a miscibility gap. When there is no miscibility gap in the phase diagram, you will never see a spinodal decomposition. So, let us try to consider a phase diagram with a miscibility gap. Something like this, alpha splitting into alpha 1 plus alpha 2. Okay. And whenever you talk about spinodal decomposition, you need to consider one aspect of stability. What is the stability? Whenever a free energy diagram, free energy curve looks like this, this phase is called a stable phase. Why? Because if I take an alloy of this composition, if this alloy wants to decompose into two different compositions of the same structure, that is what is the decomposition means. That means alpha giving you alpha 1 plus alpha 2. If this alpha, if we call this as free energy of alpha g versus x, if it splits into two, one with a lower composition, another with a higher composition, so that the overall composition remains the same. That means, if I do the volume fraction of alpha 1 multiplied by the composition of alpha 1 plus volume fraction of alpha 2 multiplied by the composition of alpha 2 should be equivalent to what? The composition of alpha with which I have started. This is what is the mass balance. As long as the mass balance is maintained, the alpha splits into some part of alpha 1, some part of alpha 2. For such a process to happen, what is the overall free energy of such a mixture? The overall free energy of such a mixture, if this is the free energy of alpha 1, this is the free energy of alpha 2, then the mixture will always have a free energy which is decided by the line joining those two. Any two free energy, any two phases having two different free energies, if you want to know the free energy of the mixture, you simply draw a line joining the two, and for the composition that of interest to you, if I choose this alloy composition having these two phases, the free energy of such a mixture is this. This is the two phase free energy. That is what we have been showing in all the phase, even earlier case also, precipitation also, whenever an alpha phase splits into alpha plus theta. So, the alpha theta common tangent that we consider, and that particular point on the common tangent gives you the two phase free energy, and the single phase free energy, if it is higher than the two phase free energy, then only precipitation will take place. We have seen that. So, this is the free energy of this mixture, and this is higher than the free energy of a single phase. As a result, such a decomposition to 2 is not usually observed, because there is no driving force for such a thing to happen. So, for a single phase alpha to split into two phases in this kind of a situation does not happen, because there is no driving force. Because of such a decomposition, the free energy is actually increasing rather than decreasing. We know that every process where there is a decrease in free energy, that is favorable, and increase in free energy is not favorable, is not it? But if your free energy curve is like this, then this alpha can split into two phases of alpha 1 plus alpha 2, and which have a free energy of this. So, from here to here it can split, and it can not only split like that, it can keep on splitting more and more. That means, the alpha 1 and alpha 2 composition will keep on deviating more and more from the alpha, and this causes further decrease in the free energy. That means, if I start with an alpha having a uniform composition in such, and if this alpha is having a free energy curve something like this at certain temperature, then what happens is suddenly this alpha is not stable, because its free energy curve is like that. So, what happens is there will be a small fluctuation, even a small thermal fluctuations. Temperature, whenever you say this particular Li is at 500 degrees centigrade, when you say this 500 degrees centigrade is a bulk temperature that you are talking about. In a small region of a nano region, you can always have a small changes, and this can cause a compositional fluctuations in such a way that there can be a small region where the composition can decrease and another region where the composition can increase. Though I have drawn it with such a scale, this can happen in a less than a nanometer scale. So, in less than a nanometer scale, if you see a small region where the atoms, because there are always atoms moving at any given temperature unless you are at absolute 0. Because of these atomic fluctuations, you can see a region where the composition goes slightly below the nominal composition in some region, and obviously those atoms have to move somewhere else. So, they go to some other region where the atoms are more than the nominal composition. Once this happens, this kind of a fluctuation is a stable fluctuation in this, because the moment such a change happens, then suddenly this region with a lower copper content, this region with a higher copper content, let us say, will be a stable couple, because that has resulted in a decrease in the free energy. But if that happens in this alloy, it will not be stable. What happens is the atoms will come back, the atoms which have the excess atoms here will come back and join the alpha, so that again the alpha will have the same composition. Whereas, in this kind of a situation, the atoms, once they come to this situation, they will not go back, because that is a stable situation. And now what happens is this particular thing starts growing. Why it grows? Because by further growing you will have a further decrease in free energy. So, this fluctuation starts with the same wavelength. The wavelength gets fixed, which may be of the order of few nanometers, and within that wavelength the amplitude starts changing. So, that means this region becomes more rich in copper, this region becomes less rich in copper, but the overall composition satisfies this. The overall composition of the Li is the same, but you will see that these compositions start increasing and decreasing, and to an extent that finally, if I take that alloy and if I am holding at room temperature this alloy, and it will keep on growing until the extent that alpha 1 achieves this composition, alpha 2 achieves this composition, and this is what you call it as, let us say, alpha 2, this is what you call it as alpha 1. The lower is alpha 1, let us say, the higher is alpha 2. So, this wave or this compositional wave will keep on changing its amplitude to such an extent that finally you reach this value, and this is what happens whenever you have this. And I have directly correlated this to this, we will see in a minute why I should correlate that to this. Okay. At the moment this and this are not really correlated. So, you will see that whenever I take a phase of this kind of a free energy diagram, you will actually see this kind of a free energy diagram in this miscibility gap, we will see it within a minute. So, but if that happens, you can see this will keep on increasing. This in comparison to the precipitation, in a precipitation the composition of the precipitate is always fixed. You start with certain fixed composition, and that during the whole precipitation process as a function of time, that precipitate composition is not changing. Only that is changing is the alpha composition will keep on changing. Whereas, here if you want to call these as precipitates, they are actually not precipitates, but these are compositional. Only when the whole growth has completed, then you will see that this would be a different composition, this would be a different composition, and this happens homogeneously throughout the sample, whereas a precipitation does not happen homogeneously. it happens heterogeneously in some heterogeneous nucleating sites, whereas here this happens throughout. Why it happens throughout? Because throughout wherever it can happen, this is stable. So, you can see a homogeneous nucleation can happen in this kind of a situation, and that keeps on growing, and this is in contrast to the what I have shown you in precipitation, where the gradient will keep on decreasing as a function of time. Here the gradient is actually increasing as a function of time. If you look at the interface, this is the, if you want to call this as one phase, this as another phase. At the interface, if you look at the gradient is actually keeps on increasing, whereas in the precipitation, normal precipitation, at the interface between the theta phase and the alpha, if you draw a gradient, and that gradient will slowly decrease, because if you remember, this is the one, this slowly becomes like this, finally it is like this. So, this gradient keeps on decreasing, whereas here the gradient initially is 0, gradient is initially 0, there is no compositional difference, and slowly the gradient starts building, and that is why some people want to call this as uphill diffusion, because the gradient is actually increasing. And this, how do I understand from the free energy point of view? Let us now try to draw the free energy curve at this temperature for this. If I draw the free energy curve actually looks like this. Am I right? Because when do you get a miscibility gap? When the delta H is positive. Whenever the delta H is positive and that is higher than the T delta S mixing term, then you will see the free energy curve will have this kind of a shape. And that, if that is the case, if I draw a common tangent, you get these 2 points, and what are these 2 points? These are these 2 points, we call them as the binodal points. Okay, they are usually called the binodal points. They are nothing but the equilibrium composition of alpha 1 and alpha 2 at that temperature. Now, if you look at this, this particular free energy curve appears to be a mixture of 2 types of free energy curve, one which is a curve like this, again a curve like this, another curve which is like this. If you look at these 2 curves, concave upwards and concave downwards. So, you have 2 parts here which are of similar in nature, which are related to stable phase condition, and there is one region here in the middle, and that is the region where there is a change that takes place of slope. If you look at the slope of this free energy curve as a function of composition, the slope here is, what is it at the pure metal end? It is minus infinity. So, this minus infinity slowly starts increasing, and when you reach this value, what is the, it is not 0, it is low, it need not be, it will be 0 only when the tangent is horizontal, tangent need not be horizontal. Okay. So, if it reaches a value, higher value. So, from minus infinity, if I now plot, in fact it would be nice if I plot it on this itself. Okay. So, anyway, so from the minus infinity it keeps on increasing, and then again you see the free energy curve, what is here, it is positive, it is positive, and then it keeps on increasing, and at some point of time this slope is changing, right. So, can you draw these slopes? Next class when we come, I want you to see how this free energy, take any such curve which has an inflection inside, draw the dou g by dou x, and then also draw dou square g by dou x square. then you will see something interesting happening. Next class when we start, we will start with that, and by the time I want you to draw and see what happens. You will see there is something which happens when you look at this part, and that is actually 0 at these two positions. We will try to see that. Okay. So, please draw a free energy curve, and for that free energy curve just below that draw this for the same scale, and below that you draw this for the same scale, and see how this changes. Okay. We will stop with that.